The negative binomial and geometric distributions. Suppose we have a sequence of Bernoulli trials with the probability of success equal to p. Let the random variable x be the number of failures that we observe before we obtain the kth success. In other words, we've determined to continue trials until we obtain exactly k successes. K could be 1 or 2 or 3, and terminate the experiment when we obtain the kth success. We count the number of failures before that kth success is obtained. And that's the random variable capital X. What's the range of the random variable X? X could be 0. For example, that happens if we obtain k successes in a row to begin with. X could be 1 failure. We could obtain a failure and followed by k successes, or 1 success, a failure followed by k minus 1 successes, and so on. X could take any non-negative integer value, 0, 1, 2, 3, and so on. Let's find the probability of the various values of the random variable x. Its probability function. The probability function of this random variable x is given by x plus k minus 1, choose x, p to the power k, 1 minus p to the power x, for x equals 0, 1, 2, and so on. Part of this probability function should seem eminently familiar. P is the probability of success, and it's raised to the power k, which is the number of successes. 1 minus p is the probability of a failure, and it's raised to the power x, which is the number of failures we observed. We'll try and explain the combinatorial symbol out front in a few minutes, x plus k minus 1, choose x. But when a random variable x has this distribution, we call it the negative binomial distribution. We'll write x tilde nb for negative binomial, k comma p, where k and p are the two parameters of this distribution. Sometimes the negative binomial distribution counts not the number of failures before the kth success, but the number of trials needed to get the kth success. This differs only very slightly from our definition of negative binomial, because the number of trials is x, the number of failures, plus k, the number of successes. So by that definition, that random variable would be x plus k in our notation. We should begin by checking to make sure that f of x is indeed a probability function. Obviously, because p is between 0 and 1, the probability function, the value of the probability function, f of x, are greater than or equal to 0. But what about the sum, as x goes from 0 to infinity of f of x? That should be 1 for a legitimate probability function. We can write that down. That's the sum of x plus k minus 1, choose x, p to the power k, 1 minus p to the power x, and we're adding over all non-negative integers x. There is an identity that's helpful here. You can verify this identity just by expanding both sides. X plus k minus 1, choose x is the same as minus 1 to the power x minus k, choose x. If we make that substitution above, then the sum becomes p to the power k times the sum of minus k, choose x, p minus 1 to the power x. And this is simply a binomial expansion. It's the expansion of 1 plus p minus 1 to the power minus k. But 1 plus p minus 1 to the power minus k is just p to the power minus k. Multiplied by p to the power k, we obtain 1. So the sum of the values of f of x is 1. Here's an example. The fraction of a very large population of males that has a specific form of colorblindness is 2%, 0.02. Suppose we randomly select men to be tested for colorblindness. What's the probability that exactly 10 non-colorblind men will be tested before we find the fourth colorblind man? This is a negative binomial problem. My objective is to obtain 4 colorblind men, and I will keep testing until I find the fourth. What's the probability that exactly 10 non-colorblind men are found before the fourth colorblind man is detected? What does this mean? It means that after testing 13 men, exactly 3 were colorblind and 10 were not. And then on testing the 14th man, that person was detected to be colorblind. So 10 out of 13 of the first 13 men were colorblind, followed by a colorblind man. The first part of that can be expressed as a binomial probability of 10 successes out of 13 trials, finally followed by 1 success. And when we multiply those, we get 13, choose 10, 0.2 to the power 4, 0.98 to the power 10. Once again, the probability of colorblind raised to the power the number of colorblind men, the probability of not colorblind raised to the power the number of such men in our sample. So if the random variable of interest is the number of non-colorblind men tested before we obtain our fourth colorblind man, X has a negative binomial distribution with K equals 4 and P equals 0.02. And what we were asked for above is simply the probability that X equals 10, the probability function evaluated at 10, and using the formula we saw in the previous slide, that's 13, choose 10, 0.2 to the power 4, 0.98 to the power 10. A second question. Suppose we're interested in not the number of non-colorblind men, but the number of men that have to be tested in order to get the fourth colorblind one. That new random variable we'll call Y. How does it differ from X? Y includes both colorblind and non-colorblind men. It's the same as X plus 4, since it includes the 4 colorblind men. Y is equal to X plus 4. And we know the probability function for X. So the probability Y takes the value little y is the same as the probability X takes the value Y minus 4. And in this case, of course, Y minus 4 must be greater than or equal to 0. And if I put that in to the probability function for a negative binomial, I obtain Y minus 1, choose Y minus 4, 0.202 to the power 4, 0.98 to the power Y minus 4, for Y equals 4, 5, 6, and so on. It's quite easy to distinguish the binomial distribution from the negative binomial by the context of the question. For example, for the binomial distribution, we specify in advance the total number of trials. That's a fixed number, usually called little n. What's unknown in the case of the binomial in advance of the experiment is the number of successes. This is only determined by running the experiment and counting the random number of successes. For the negative binomial, by contrast, the total number of trials is not known, is not specified in advance. We don't know how many trials will be required until after the experiment is completed. The number of trials is random. What we've specified in advance is the number of successes we wish to see, a total of k. And we've resolved to continue with trials until we get exactly k successes. Otherwise, these two distributions are similar. They both depend on Bernoulli trials, independent experiments, each of which has the same probability, p, of a success on each trial. One case of the negative binomial is particularly simple, and that's called the geometric distribution. It's the special case when k is equal to 1. In this case, the random variable of interest is the number of failures we obtain before the first success in a sequence. We obtain the probability function of a geometric by just setting k equals 1 in the negative binomial. And in this case, the probability function is f of y. The probability that y takes the value little y is p times 1 minus p to the power y. It's p to the power 1 because we observed one success. It's 1 minus p to the power y because we observed y failures. And in this case, we'll write y is geometric with parameter p. And as usual, let's check first that f of y is a legitimate probability function, that its values are non-negative and add to 1. The non-negativity is easy, and if we sum y goes from 0 to infinity of f of y, that turns out to be the sum of p times 1 minus p to the power y, and that's just a geometric series. You all know how to add a geometric series. The infinite sum is the first term divided by the common ratio, the quantity that we multiply by one term by to get the succeeding term. So it becomes, in this case, p times 1 over 1 minus p. That simplifies to the value 1, provided, of course, that p is strictly positive. What can we say about the cumulative distribution function of a geometric random variable y? Again, given that we know how to add a geometric series, this is easy to obtain. Let's first calculate the probability that y is bigger than little y. And we do that by just adding up over all of the values from y plus 1 to infinity their respective probabilities. P times 1 minus p to the power x. Again, like the last, that's a geometric series. And the sum is the first term in the sequence, which is in the series, which is 1 minus p to the y plus 1, divided by the common ratio, 1 minus p. And that simplifies to 1 minus p to the power y plus 1, But we weren't asked for the probability capital Y is bigger than little y. The CDF is the probability capital Y is less than or equal to little y. That's 1 minus the probability we've just calculated because it's the complement of the event. That's 1 minus p to the power y plus 1. And once again, y can take the values 0, 1, 2, any non-negative integer value. Here's an example involving the geometric distribution. A textbook printing line is undergoing inspection for printing errors. Suppose the probability of finding a printing error in a textbook is 20%. If the textbooks are inspected randomly, what's the probability that we'll need to look at least 10 textbooks to find the first one with a printing error? This again is a simple application of the geometric distribution. If y is the number of error-free textbooks we need to inspect before we find one with a printing error, then it's the number of failures before the first success. Y has a geometric distribution with parameter p, and here p is 0.2. We're asked for the probability that y is greater than or equal to 9. The probability at least 10 textbooks are checked is the probability that at least 9 error-free textbooks are checked before the first one with errors. So y is greater than or equal to 9. That probability is 1 minus the probability y is less than or equal to 8, which is 1 minus the sum of the probability function from y equals 0 up to 8, or 1 minus p to the power 9. We could have known in advance that this would be the answer. The probability that we need at least 10 textbooks to be checked is the probability that the first 9 are all error-free. The probability any one textbook is error-free is 1 minus p. The probability that 9 in a row are is 1 minus p to the power 9. Here's a problem. Masher Joe Steroid plays center for the University of Canola football team. He's doing a postgraduate certificate in advanced locker management. And in order to be eligible to play football, he's required to take one course every quarter until he's passed a total of 5 courses. Regrettably, his memory has suffered from a doubtful-looking cold remedy he's taking, and his probability of passing each course is exactly p equals 0.3, regardless of whether or how many times he's taken that same course. What's the probability that he has to take the course Statistical Methods for Locker Managers more than 3 times in order to pass it? Let's define x to be the number of failures before his first success in this course. Then x has a geometric distribution. The parameter p of that geometric distribution is 0.3. We're asked for the probability that more than 3 attempts are required. That's the probability of more than 2 failures. The probability that x is greater than 2. Again, we can obtain this by adding up the probability function from 3 to infinity, the sum of p times 1 minus p to the power x. And again, that's the sum of a geometric series. It sums to 1 minus p to the power 3, which in this case is 0.343. Joe can be reassured by the relatively small 34% probability that he'll have to do this course more than 3 times. In order to get his certificate, Joe needs to pass 5 courses. What's the probability that he can do that with fewer than 20 failures in total? Again, this is a question involving the negative binomial distribution. X is the number of failures before his 5th success. X has a negative binomial distribution with parameters k equals 5 and p equals 0.3. And we're interested in the probability of fewer than 20 failures, the probability that x is less than 20, which of course we can get by adding up the probability function as x goes from 0 up to 19. Sum x goes from 0 up to 19, x plus 4, choose x, because it's normally x plus k minus 1, and k is 5. P to the power k, or 5. 1 minus p to the power x. And that sum in this case, where p is equal to 0.3, is something like 0.889. Again, he can be reassured that there's almost a 90% chance he'll get by with fewer than 20 failures. Review question. The St. Agatha Lottery. Each one of the 5 members of your immediate family purchased a lottery ticket for the St. Agatha Lottery and a chance to win an all-expenses-paid trip to beautiful downtown St. Agatha. If there are 100,000 tickets sold, of which 1% are winning tickets, What's the probability that exactly one member, one of the 5 members of your family, wins a trip? The second question, the lottery becomes weekly, and every week 1% of the tickets win a trip. You are desperate to visit St. Agatha, and you decide to purchase 1 ticket every week until you win such a trip. What's the probability that you will need to purchase more than 100 tickets before winning? You should pause and work out these solutions. Solution. Suppose there are 100,000 tickets sold, of which 1% are winning tickets. What's the probability exactly one member of your family wins a trip? Well, the fact that there are 100,000 tickets sold indicates that the winning tickets are unlikely to vanish as you buy your 5. Whether you sampled with or without replacement makes virtually no difference to the distribution in this case. So it seems reasonable to use a binomial distribution for the number of winning tickets in your family. Binomial with parameters n equals 5, you purchased 5, and the probability of any one ticket being a winning ticket, p equals 0.01. So the probability x equals 1, according to a binomial probability function formula, is 5 choose 1, p to the 1, 1 minus p to the 4. And replacing n by 5 and p by 0.01, we obtain 0.048. A little less than 5% is the chance that one person in your family will win a ticket. You've decided to purchase a ticket every week until you win. What's the probability you'll need to purchase more than 100 tickets? In this case, the number of weeks that you purchase a losing ticket before winning, y, has a geometric distribution. P is 0.01. We're asked for the probability y is bigger than 99, the probability you lost, in other words, the first 100 weeks in a row. That is 0.99 raised to the power 100, or somewhere around 0.366. Here's a second review question. What distribution do I use in each of the following scenarios for the random variable x? And our choices are those we've studied so far: geometric, hypergeometric, binomial, negative binomial, uniform, and so on. The first question. We sample without replacement from a population of r s's and n minus r f's, and we count how many s's we obtained, successes, in a sample. The second question is identical, except that we sampled with replacement instead of without replacement. The third question, I sampled with replacement until I obtained exactly k successes. We counted the number of failures we obtained before getting the kth success. And the fourth question, I sampled with replacement until I obtained 1 success, and we counted the number of failures before that happened. Pause and answer these questions yourself before proceeding. The answer to the first question is a hypergeometric distribution because we sampled without replacement from a finite population and counted the number of successes. The second question was identical except that we replaced after each draw, and so the trials were independent of each other. The distribution for x here is binomial. In the third question, we sampled until we had a fixed number of successes. We counted the number of failures. That's a negative binomial. And again, in the fourth question, it's identical except that the number of successes was to be 1. The number of failures before the first success now has a geometric distribution.